You guys, we'll get started in a couple minutes. I'm just gonna wait a couple more minutes to let other people in, and then we'll get going.
Okay.
Why are you not back? My phone. Sorry.
How are you guys today? Good? Can you guys hear me? Can you guys hear me?
Yeah.
Yeah.
Okay. Is there a delay? It seems like there's a delay. Okay. Hang on one second. I guess the first thing I want to do is kind of open the floor to questions. Well, I guess the first thing I want to do is just kind of go through a little bit of functionality with the Zoom. For those of you who had me for lab yesterday, this might be a little bit of a repeat, but if you look in the bottom right-hand corner of your screen where it says more, and then just to the left of that, or yeah, just to the left of that, it says reactions. You guys can give me a thumbs up. And so like if I ask a question, giving me a thumbs up kind of lets me know that you're with me, you know what's going on. I did not find the raising your hand functionality. I'll have to do some more investigating with that. But you should be able to raise your hand. I will look and figure out what's going on with that. I haven't figured it out yet. The other thing you can do is you can chat. So You can message me and you can message everyone. Are you guys able to message each other, or is that just available to me?
No, you're able to message anybody.
You can message anyone in the group?
Um,
Okay. Be nice to
Yeah.
me. Okay. So yeah, you guys can talk to each other and stuff. And one of the things I wanted to talk about that I sent out was I think it would be helpful for you guys to get in small groups, whether that's your lab partners and then maybe one or two other people or whatever works for you. If you have kind of a small group of people you stay in touch with, can bounce ideas off of or whatever, I think that might be helpful to you, which it's very possible you're already doing that, which is great. Okay. Like I told my lab group yesterday, you know, a lot of based on this situation, a lot of the responsibility is going to be on you guys to kind of keep up with what's going on. And I'm aware of that. And again, as I told my lab group, you know, I'm going to try and be as flexible with you guys as I can. But we do still have work to do, and we're going to have to do it. So we're kind of all in this together, and hopefully we can make the best of it. If you noticed in the assignments, so I want to kind of talk to you a little bit about Blackboard and what I've got set up there. In the tabs, there's information, and I posted a couple things for you guys already. That was kind of general information as I was coming up with it. Again, in terms of lecture, we're going to meet as scheduled. I will be recording them, so they will be available to you if you can't make it during the scheduled time or whatever. So it shouldn't be that big of a deal. I think it's going to be more useful to you if you actually come during the scheduled time. But if you can't make it, then that's available to you as a backup. Okay. I did post 2 assignments. Those are both lab assignments, and you should be able to post those to Blackboard now. I know I've started getting some, and you should get confirmation that it's posted. I had an issue with one lab yesterday, and if it doesn't come through as a readable document to me, I will definitely email you and say, hey, this didn't work, try again or something. But you can post it as a picture. You can scan it, or you can send an electronic copy. Any of those should work. I just, again, need to make sure that it comes through readable to me. Okay. In terms of the lab, for those of you who have lab on Monday, again, you've already done this. Okay. We did the copper lab, whereas the Wednesday people actually got to do that one in the lab while we were still on campus. But what I posted is lab videos. There's one up there for the copper lab for the Monday people, and I would say that actually went pretty well yesterday. Hopefully you guys feel sort of at least kind of the same. But I kind of went through the lab and talked about some different things. Now for the lab coming up, the next lab, the titration lab, I actually posted 3 separate videos. So there's a video of a guy actually doing a titration experiment. There's a video of me kind of talking you through the lab. And then there's another video. It's an Alex video. I don't know if you guys are familiar with that or not. That's an online learning system. And they kind of walk you through a problem where the goal of that lab is to find the molecular weight of an unknown acid. And they kind of walk you through that problem. Okay. So 3 separate videos. And again, what I've done in terms of scheduling is Monday lab is from 3 to 6. So I've left that first hour kind of free for you guys. to do the lab in terms of watching the videos and stuff and maybe answering pre-lab questions and stuff like that, certainly you're free to do it before then. But then we'll kind of meet the second hour of lab, starting the second hour of lab. So Monday, that'll be 4 o'clock. For the Wednesday lab people, we'll set up a Zoom meeting starting at 1 o'clock. Okay, again, giving you a chance to watch that stuff and come up with the questions and things. Yesterday's lab, now the lab was pretty simple in terms of data and stuff. Really all you were doing was starting with a massive copper, ending with a massive copper, and calculating your percent recovery. So in terms of calculations, it was really not that intense. That Zoom meeting only lasted, I think it was just over 20 minutes. So just to give you an idea, that was probably the shortest one that we're gonna have, but it also may have been a little longer due to me kind of explaining some things at the beginning, kind of like I'm trying to do now. Okay, so my guess is those meetings will last anywhere from 20 to 40 minutes. That is a guess. Some might be shorter, some might be longer. Okay. In terms of lecture, give me a thumbs up. Did you guys notice that I posted the lecture notes on Blackboard? Yes. Yes. Thank you. Feedback is good. I appreciate it. Okay. Were they readable to you guys? Pretty decent in terms of readability.
I'd say so.
Okay.
I'm one
So
person.
that's kind of how I'm going to do it. Now, since you have the notes in advance, that's going to be a little bit of a time saver for us in terms of going through stuff. So I don't know how long we're going to meet. And instead of an hour and 15 minutes, it might be more like an hour or something. We'll just kind of see how we go. I'll definitely in person, I can get an idea of when you guys are done for the day. Some of you might be done before you start, but you know, I'll try to get a sense of, hey, that's enough for the day. We'll call it, whether that happens after an hour or whatever. Okay. As it stands now, the notes I've given you, those are the notes I want to get through for our next test. I don't have a date specifically in mind. I do anticipate coming up with that fairly quickly. Just off the top of my head, I'm guessing either 2 weeks from today or 2 weeks from Thursday will be your exam. Okay. I have not adjusted the dates in Newton yet for due dates. I will get to that. It's on my list today. Okay. So that's coming. All right. One more thing that, and again, you guys can type in a chat if you have questions. Okay. Type in chat if you guys have questions. One question I did get, someone asked me about lab stuff. Okay, in terms of a lab key, if you checked out of your dorm and turned in your lab key, that's great. If you didn't, I sent you a note about a lockbox being available on campus. I know that's not practical for some of you. I think we might be sending, it's not quite determined yet how we're gonna handle the rest. We might be sending out business reply envelopes. Throw your key in there, probably in between a note card or something, and then stick it in the mail. Okay. So that's a little bit up in the air right now. If you haven't turned in your lab key, we're definitely going to do our best to get them back. The other issue is for a lot of you guys, we have stuff of yours. The way we're going to handle that, I think the guy in the stockroom is going to go through all the drawers, mark what the lab drawer number is, and then he'll be able to match it up to a name, and you'll be able to get your stuff eventually when we go back on campus. Okay. Whether that's in the summer or it ends up being next fall. Okay. If you're not taking classes in the summer, that's fine. It'll be available to you next fall. Okay. Okay. A couple questions. Someone said in lab yesterday, yeah, so that's to everyone. In lab yesterday, you said to disregard the oxidation questions for the copper lab. Does that mean oxidation won't be on the test? What I'm going to do with that, I am going to go over it very briefly with you guys. In the end, I will probably ask Newton homework questions on it. And then what I'll end up doing is I'm planning on giving extra credit for those questions. So if you answer them in the lab, you can get a point or two of extra credit. Okay. So hopefully that takes care of that. Someone said here, if you click on participants, raise hand is on there. I still don't see it. Are you guys able to see it? Oh, I see it now. Okay. Okay, so are you guys testing it out or are you guys raising your hand? And I can't see all 28 of you at once, so I'm hoping if people raise their hand, they kind of pop up to the top. So Rachel, did you have a question? Or were you just testing raise your hand?
No, I was just testing it.
Okay. Cassidon, do you have a question?
No, I was just testing it.
Okay, okay. Anybody have a question? Okay. All right. Any question in terms of functionality, how this is going to work going forward? Wednesday lab people, you haven't had lab yet. You will tomorrow. I would say I'm pretty happy with how things went yesterday in Monday lab. 20 out of 23 people showed up, and I was pretty happy with that. Today for lecture, we've got 28 out of, I think there's like 45 of you in there. Okay, so I would hope for a little bit better, but it's okay. Like I said, these will be recorded and available to you. I think it will serve you better if you're here, if you can be. And if you can't be, the backup plan is to have things recorded. So they will be available to you. All right. Any questions on anything on Blackboard? Any questions on any functionality? The other thing I want to remind you guys of, and again, for those of you who had lab yesterday, I'm repeating myself. You guys hit me with emails and stuff. Like I said, a lot of the responsibility is on you, and hit me with emails. I'm expecting them, okay? And I will try to get back to you in as timely a fashion as possible. I'm not going to be super formal. I'm probably not going to address you. I'm probably not going to sign my name. I'm going to give you a quick answer, and if one of the Microsoft auto answers works, that's probably what I'll click and hit send, okay? So the other thing is I am going to set up some office hours. I haven't quite got that figured out yet in terms of times. But I'm going to take care of that sometime after today, where you'll have a chance to, if you have a more detailed question, obviously some questions I can't answer by email. An office hour would work better for that. So it'll be a chance for you guys to kind of get immediate feedback from me if you have questions on stuff. Okay. All right. Anything else? So again, email me. Don't feel like you're bothering me. That's not going to be the case. I will try to get back with you as quick as possible. So I have a note. Whitney raised your hand. Were you testing?
Yes.
Okay. Okay. All right. So what I'm going to do now, and we're going to see how this works. I am not an expert in Zoom. Okay, I'm going to try to switch over to lecture notes. I need you guys to tell me when that's what you see. All right, so give me a second here. Come back here, share screen. Are you guys seeing my Blackboard site now?
Yeah.
A thumbs up?
Yeah,
Yes, no?
yeah.
Yes? Okay, good.
Yes.
Okay. So I'm going to go to lecture notes. Okay, so this is going to be another thing that helps you as well. If you have a question, literally you can say, hey, on page whatever of the notes. So I numbered them up here. So can you guys see when I'm circling the number with my arrow? You guys see like the cursor circling the 1, or is that only visible to me?
No, we can see it.
You can see it. Okay,
I
thanks.
can't see it.
You can't see
I
it?
saw it.
You guys see my,
I didn't see it. I was just lagged out.
Wait,
okay,
yeah, I
there it is.
did.
There it is.
see it now?
Yeah.
Okay. I did
Bit
get
of
a
a
pop-up
delay.
that said my internet was unstable for a second. So hopefully it gets better. Okay. Anyway, like I told you guys, we had gotten through. Hopefully these notes are familiar to you. We had gotten through this stuff. Here's the oxidation reduction reactions on page 8. Okay. And so you can kind of review those. Again, I'm going to come back to those. I am going to assign those on Newton, but they won't be on your Newton test and they won't be on your exam either. Okay. But if you kind of go through those and work through those and answer those oxidation number questions on the lab, I will count those as extra credit. All right. Okay. So, why isn't this opening? Okay. Actually, I need that page. Okay, so do you guys see my page 10 right now?
Yeah.
Yes.
Yes.
Yep.
Okay, so here's where we're going to start. Chapter 4. And we're just going to kind of walk you through this, okay? So if something needs explained, then what I'm going to do, I'm going to do this. I can go to a whiteboard. Now, I will tell you, I am terrible at writing on this thing, and it kind of does. So it doesn't, do you guys see that note?
Yeah.
Yes. Yep.
Okay. So one of the things about this that I don't like is, like, if I write H2SO4 on here or CaCl2, it doesn't subscript for me. And in fact, even if I have that loaded into a Word document, when I bring it over here, it takes it back to that. So there's going to be some notation things that are not going to be great. You might have noticed that for those of you who did the Copper Lab. That's what I could do with it. So anyway, coming back to the notes. Okay, so what we're going to talk about is we're going to talk about chemical reactions, calculations involved in chemical reactions, That generally is referred to as stoichiometry. Okay, so I kind of like to call stoichiometry chemical math. And what we're doing in stoichiometry is we are looking at calculating the quantities of chemicals that are involved in a chemical reaction. All right, so to give you an example of that, just starting with kind of a simple chemical reaction, what we've got, and do you guys, when I circle this, do you guys see that?
Yeah.
Yes.
Yep.
Okay, because it kind of changed on me. All right. So just as an example of a chemical reaction, we have nitrogen. Remember, nitrogen is one of your diatomics, so N2, reacting with hydrogen, H2, to give us NH3. We know that chemical reaction occurs. We know nitrogen's diatomic. We know hydrogen's diatomic, and we know the formula of NH3, or the formula of ammonia, is NH3. Okay, so some of the stuff, this is an example of, like, if I was doing this in class, I would have written on the board N2 plus H2 gives me NH3. And when we have a balanced equation, what's the first thing we need to do with it? Balance it. So we need to balance our chemical equation, right? So just remembering, no, it's been a little while. So what we want to do is we want to change the coefficients out in front. How many nitrogens react with how many hydrogens to give me how many ammonias? Okay. So if you remember, our requirement is we want lowest whole number coefficients possible, and we want the same number of each kind of atom on both sides. So for this reaction, it turns out that happens when we have 1 N2 reacting with 3 H2 to give us 2 NH3. Okay. So where are we? Right now we have a balanced chemical equation. Okay. So what we want to be able to do is we need to know what that balanced chemical equation is telling us, right? So what that balanced chemical equation is telling us is it's telling us this balanced chemical equation is the same thing as this statement here. Okay, it's just a more concise way of saying it. What is it telling us? It's telling us that 1 molecule of nitrogen and 3 molecules of hydrogen, I don't care how you interpret this, I say reacts to form. You can say yields or gives or however you want to interpret it. Gives us what? It gives us 2 molecules of ammonia. All right, so that is what the balanced equation is telling us. Now, what if, and I can use any number here, what's true if I have 10 molecules of nitrogen? If I have 10 molecules of nitrogen, how much hydrogen is involved? 30, right?
30. Yeah, and then
30
you get 20.
hydrogens. And you're going to get 20 NH3s. Okay. Why is that? The ratio always stays the same. So the ratio is 1 of these and 3 of these gives us 2 of these. Okay. So if I have 10 of these, I need 30 of these to give me 20 of those. If I have 100 of these, I need 300 H2s, and I'll get how many? Someone tell me.
100.
200 NH3s, right? Okay. Ratio is always 1 to 3 to 2, and that ratio is coming from the balanced equation. Okay. What if I have 6.02 times 10 to the 23rd nitrogens? How much hydrogen do I need?
3 times the
3
Avogadro.
times that, right? So I need 3 times 6.02 times 10 to the 23rd of hydrogen. And that's going to give me 2 times 6.02 times 10 to the 23rd of NH3. What's another way of saying that? What is 6.02 times 10 to the 23rd N2s? 1 mole, right? So 1 mole of this reacts with 3 moles of this to give me 2 moles of that. Okay. So when you have a balanced equation, you can interpret it either in terms of molecules or moles. Both are valid interpretations. So again, just looking at this thing before we go on, 1 mole of this and 3 moles of this react to give me 2 moles of this. Or 1 molecule of this and 3 molecules of that react to give me 2 molecules of that. Okay, both of those are valid interpretations. All right. Okay, did it switch now? Are you guys seeing page 11?
Yeah.
Yes.
Yep.
Okay, great. Okay. So first question. Again, we're still using that balanced equation. What if I have 3.85 moles of N2? 3.85 moles of N2 is going to require how much hydrogen?
3 times that.
3 times that. And I'm going to get how much NH3? 2 times that. So it doesn't matter what this number is. If this number is in terms of molecules or moles, that ratio, and I don't have it written here anymore, but it's 1 to 3 to 2. That ratio holds true for any amount. This amount doesn't matter. I happen to use moles. What does matter, though, is you have to be either in terms of molecules or moles for that thing to work. You can't be in terms of grams. That gets a little more complicated. We have to use our mole to gram conversion, which hopefully we remember from our mega spring break. Okay. All right, so like it says here, based on the coefficients in the balanced equation, any 2 chemicals can be related to one another based on those coefficients. Again, for our reaction, it's 1 nitrogen, 3 hydrogens, 2 NH3s on the product side. Okay, so what we can do with those things is we can kind of set them up as conversion factors. Based on our balanced equation, what do we know? We know our equation tells us for every 1 mole of N2, 3 moles of that should say H2 are involved. Okay, so for every 1 mole of N2, 3 moles of H2 are involved. That's a valid conversion factor specifically for that chemical reaction. If this is a valid conversion factor, what else is a valid conversion factor? The reciprocal of that thing, right? So I can also say there's 3 moles of H2 for every 1 mole of N2. Which one do I want? Well, it's kind of going back to like inches to centimeters and centimeters to inches. What you want depends on what you're given and what you're looking for. Okay, so this relates nitrogen to hydrogen for the equation. We can also say for every 1 mole of N2, there's 2 moles of NH3 involved, again, based on the coefficients. So we can use this as a valid conversion factor. And if that's a valid conversion factor, again, the reciprocal of that thing is also a valid conversion factor. Okay, and then tying hydrogen to NH3, the relationship there is 3 moles of H2 for every 2 moles of NH3. Where am I getting these numbers from? This 1, this 3, this 1, this 2, this 3, this 2. Where are they coming from?
The chemical equation.
The coefficients from the balanced
and the-
chemical equation, right? So,
Yeah, and the ratio.
okay. Do you guys have questions on these conversion factors or where they're coming from? I have lost part of my screen, so I'm not sure I'll know when you raise your hand. I don't see my chat, for example. I'm hoping it'll pop up if someone chats a question. Okay. Any questions? Okay. Let me scroll through here. That's not what I wanted to do. Okay. All right. So based on that now, let's look at some problems. How is this going to show up in a problem? All right. Again, we're still looking at our same balanced equation. And so the sort of first or simplest sample problem is, okay, we've got a balanced equation. I want to know how many moles of NH3 can be made from 5.5 moles of H2. All right. So these are going to be conversion factor problems. And how do we do conversion factor problems? If I'm trying to convert inches to miles, what do? You always start with the given quantity, correct? So I'm given 5.5 moles of H2. I'm looking for moles of NH3. So here I am starting with 5.5 moles of H2. I need to know how much NH3 is involved, okay? How do I relate NH3 to H2? I look at my what? Help me out here. Balanced equation? Yes?
Yes.
Yes, thank you. Okay, participation's good, I appreciate it. All right, so what does my balanced equation tell me? Again, the only two things involved here are NH3 and H2. My balanced equation tells me, and again, it's not on this page, but you should have it previously. I get 2 moles of NH3 for every 3 moles of H2. Is this conversion factor set up correctly? How? Yes, no, how do I know? Give me a thumbs up if
Yes,
you think it's
because-
right.
Mm,
Okay. It's right. How do we know it's right?
Because you want the moles H2 to cross out.
Exactly. Moles of H2 will cancel, moles of H2 on top, cancel moles of H2 on the bottom. You end up with moles of NH3, which is what you're looking for. So unit wise, that's what you're going to get, moles of NH3. Okay. So crunching through that on your calculator, 5.5 times 2 divided by 3. Numerically, we get 3.7 moles of NH3. And that's our answer. We're done. That was a one-step process. Okay. So this is where that conversion factor comes into play. And again, let me just go to the whiteboard here for a second. If you remember our list of important conversion factors, kind of our new important conversion factors is you can go from, I'm going to say moles of X to moles of Y. So just generically moles of one chemical to moles of another chemical. And to do that conversion factor, you use the balanced equation. Okay. So specifically the coefficients from the balanced equation allow us to convert from moles of one substance to moles of another substance based on the balanced equation. For those of you who did the Copper Lab, I kind of had this on your list of important conversion factors, which hopefully you remembered from stuff before spring break. Okay, let's come back here. Okay, any questions on that example problem? Again, going from, we had moles of H2, we calculated moles of NH3. Any questions on that? Okay, again, I'm not seeing my full Zoom window, so I'm assuming if a chat comes up, I will see it. All right, so next thing we're gonna do, we're gonna take that one step further. And let's say we wanna know how many moles of NH3 can be made from 8.51 grams of nitrogen. Okay, so again, this is a conversion factor problem. We're gonna work it the same way. In terms of start with our given quantity and work through it using our valid conversion factors to figure out what we get. Okay. So what do I have? I have 8.51 grams of nitrogen. I'm going to start with that. And what do I want to end up with? I want to end up with moles of NH3. Okay, so same thing when we did, say, inches to miles conversion. Number one, there's more than one pathway to get there sometimes. And what you want to do, you can, if it helps you, write out your scheme. Okay, so I'm going to go back to this real quick. We have grams of NH3. Do we have grams of NH3? Is that right? We have grams of nitrogen.
Yeah, we have grams of nitrogen.
Grams of nitrogen. Okay, so kind of figuring out our scheme, we're going to go grams of N2 to
Moles.
moles of N2. Okay, can we do that?
Yeah.
Yes. And how do we do that? We use the molecular weight of N2, right? So from grams of N2, go to moles of N2. And then from moles of N2 to what?
Moles of NH3.
Moles of NH3. And can we do that?
Yes.
Yes, we can do that based on what we just talked about, the mole to mole conversions. Okay. So this is kind of going to be our scheme. Again, especially starting out, if it helps you to write out your scheme, write out your scheme. If it doesn't help you, don't do it. Just go. Okay. All right. You get back here. Okay. So I have grams of N2. From grams of N2, I want to go to moles of N2. To go from grams to moles or moles to grams, what do? I use the molecular weight off the periodic table. All right. So nitrogen's 14. It's diatomic, so N2 is 28. Reminding you what that tells us. What does that tell us? It tells us a single molecule of nitrogen has a mass of 28 AMUs. 1 mole of nitrogen has a mass of 28 grams. Okay, so that's where this conversion factor is coming from. That gets me 2 moles of nitrogen. Then once I have moles of nitrogen, it says here, the conversion factor I want is 2 moles of NH3 for every 1 mole of N2. Someone remind me where these numbers are coming from?
Balanced equation.
The coefficients from the balanced equation. I have one person with me and I'm going to take it. No, hopefully you guys are all following along. Any questions on this conversion factor?
Nope.
Okay, so you go to moles of N2, and then from moles of N2, you go to moles of NH3, again using the coefficients in the balanced equation. And unit-wise, grams on top, grams on the bottom, moles N2, we end up with moles of NH3, which is what we want. Crunch that through your calculator, and what you should get is you get 0.608 moles of NH3. All right, so should verify that. It would be ideal if you guys did some Newton work. Again, I'm going to adjust your due dates for homework to be the third exam date, which I'm anticipating being, I don't know what that date is, but 2 weeks from Tuesday or 2 weeks from Thursday. Okay. Anyway, so try some of these problems out on Newton to verify that you're getting or understanding it and that you are where you need to be. All right, next problem then. Next problem, how many grams of NH3 can be made from 10 grams of H2? Okay. So kind of talking you through your scheme here, and it's written out here. Our scheme is going to be what we have, grams of H2. We want to eventually end up with grams of NH3. How are we going to get there? Our scheme is going to be from grams of H2 to moles of H2. Can we do that? Yes. Okay. Then from moles of H2 to moles of NH3. Can we do that?
Yes.
Yes. And then from moles of NH3 to grams of NH3. Can we do that? Yes.
Yep.
Okay. So that's our scheme. So from there, it's a matter of plugging in and seeing how it goes. Okay. All right. So again, starting with what we're given, 10 grams of H2. From grams of H2, I go to moles of H2 using molecular weight off the periodic table. Again, hydrogen's 1, so 2 of them is 2. That gets me to moles of H2. From moles of H2, I'm going to go to moles of NH3. And so these, again, come from the coefficients of the balanced equation, and I get moles of NH3. And then from moles of NH3 going to grams of NH3. Looking on the periodic table, nitrogen is 14. Hydrogen is 1, 3 of them is 3, so 14 and 3 gives me 17 grams per 1 mole. And when I crunch through that, what I find is that from 10 grams of hydrogen, I expect to make 56.7 grams of NH3. Okay. Now let's talk about that for a second. If I have 10 grams of hydrogen, can I for sure get 56.7 grams of NH3? I'm going to say the answer to that question is no, because what? I need something else too, right? I need some nitrogen to make this reaction go. I can't just magically convert 10 grams of H2 to 56.7 grams of NH3. I need some nitrogen. If you think about it, you can actually calculate how much nitrogen you need by conservation of mass. If 56.7 grams of NH3 can be formed from 10 grams of H2, you're going to need 46.7 grams of N2 to make that go. And you can either just do that by different subtraction here, or you could take this 10 grams of hydrogen, do this same calculation for N2, and what you would do is you would find you need 46.7 grams of N2. Okay, so a couple scenarios. Let's say you have 46.7 grams of N2. If that is the case, then what happens? With my 10 grams of hydrogen, if I have 46.7 grams of N2, what should happen? I'll get my 56.7 grams of NH3. I will have no N2 left. I will have no H2 left, because those are the two amounts that are needed to react together to get me to this 56.7. So I don't have leftover of anything. Okay. If I have less than 46.7 grams of N2, what I'll get is I will get less than 56.7 grams of NH3. And I will have some H2 left over, because I could have reacted with as much as 46.7 grams of N2. So if I don't have that much there, some of this is going to be left over. It's not going to have reacted or paired up to give me my optimal amount. Okay. And then the next case is if you have more than 46.7 grams of N2, you will get your 56.7 grams of NH3, but since you have more than you needed, you could have reacted with more H2, so any amount of N2 over that 46.7 is not going to have anything to react with, and it's just going to be left over. Okay. Does this make sense to you guys?
Yeah.
Yeah.
Okay, so you can kind of figure out, we kind of figured out we needed 46.7 grams. Essentially, our possibilities are we have that amount, we have more than that amount, or we have less than that amount. And these are the scenarios that are going to happen based on that. Okay. Okay. So kind of some things to talk about in terms of those calculations then when we're trying to relate chemicals to each other in terms of reactions. When we did our calculations, previous calculations, we made two assumptions. Okay. First assumption was that the reactions go to 100% completion. In other words, what we mean by that is all of the reactants that are available react and go to products. Okay. That's not always true. In fact, it's rarely true. A couple things can happen. First of all, you can have side reactions occurring where you don't get the expected or desired product. You can have unreacted starting material. If you think about it, as they react, their concentration becomes less and less. They're less likely to run into each other and have a reaction. Okay, so those are kind of the two big things. So you can have unreacted material. You can have side reactions. Okay. Kind of an example of a side reaction is like if you use natural gas to heat your home. Natural gas is mostly methane. What do we do to that methane? We burn it, right? So ideally what we'll get is we'll get carbon dioxide and water, and we'll get heat as a byproduct. An undesirable side reaction there is you can possibly get carbon monoxide. That's not good, okay? So side reactions do occur sometimes. That's an example of you wouldn't get a complete reaction. Okay, so that's one assumption, and we'll talk about that. This actually kind of ties in with, on the Copper Lab, you guys calculated percent recovery. More generally, we will refer to that as percent yield. How much product should we have gotten compared to how much product we actually did get. Okay. The second assumption we're making, and we kind of just addressed this with the nitrogen, we're saying that for a given amount of one reactant, we assume there's enough of the other reactant to make the reaction go. Going back to our problem here, how many grams of NH3 can be made from 10 grams of H2? We said we could make 56.7 grams of NH3. Okay. Again, that's not for sure. We calculated for that to happen, we would need a minimum of 46.7 grams of N2. We didn't say anything about N2, but in doing this calculation, we assume that it's there. Okay. We're going to lose that assumption very quickly. All right. So to kind of talk about that, what I want to talk about is what's known as a limit. You'll see this both ways. I usually say limiting reagent. You might also see that as referred to as a limiting reactant. And what that is the reactant that is entirely consumed when a reaction goes to completion. Okay. And you'll understand this lesser number when we do an example. Okay. What the limiting reagent does is it determines the maximum amount of product that can be made. Okay. Do be a little bit careful about this word maximum, and again, we'll see that when we go through an example problem. Excess reagent or excess reactant is a reactant that is not entirely consumed when a reaction goes to completion. Okay. So an analogy I like to use for you guys, just because it's easier to sort of grasp, visualize, is I like to use the example of making cars. Okay. And obviously this is oversimplified, but to make a car, what do I need? I just have three components here. I need one engine. I need 4 tires. I need 2 doors to make my one car. This is analogous to chemical reactions. Whereas in our equation, we needed 1 hydrogen and 3 nitrogens to give us 2 NH3s. Those coefficients out in front are analogous to coefficients in a chemical reaction. Okay. So fundamentally, the question you should be asking yourself, because kind of the question we're working up to, going back to this for just a second again, when we said how many grams of NH3 can be made from 10 grams of H2, that's a simpler problem because you don't take into account the nitrogen. Okay. The problem we're working up to is I'm going to say how many grams of NH3 can be made if I have, and I'm just going to use different numbers here, 20 grams of H2 and 70 grams of NH3. Then we need to take both into account to figure out where we're going to get. Okay. All right. So kind of as a prelude to that, looking at this example, and again, oversimplification, we're just looking at 3 components here. 1 engine, 4 tires, 2 doors gives us our 1 car. Okay. So let's say in that particular day in the Toyota plant or whatever, I have 25 engines, I have 160 tires, and I have 40 doors. The question is, how many cars can you make based on having that inventory? So what you do is from each component, engine, tires, and doors, the question you should be asking yourself is how much product can you make? So what do? We call up the engine guy and he says, I have 25 engines today. And he says, based on having those 25 engines, I get 1 car for every 1 engine. I can make 25 cars today. Okay. Then call up the tire guy. The tire guy happens to have 160 tires that day. Okay. From his 160 tires, you get 1 car for every 4 tires. Based on that, you could possibly make 40 cars that day because it's a 1-to-4 ratio. Okay. Having 40 doors, assuming all 2-door models, you get 1 car for every 2 doors. From your 40 doors, the door guy says, I can make up to 20 cars today. All right. So, what do you get? Do you get 25 cars? Do you get 40 cars? Do you get 20 cars? Do you add those all together? Do you multiply them? Do you take the cubed root of that?
You get 20 cars.
You get 20 cars, right?
20 because it's the least number.
Yes. So from the engines, you could have possibly gotten 25 cars. From the tires, you could have possibly gotten 40 cars. From the 40 doors, you could possibly get 20 cars. What happens once we get 20 cars?
You run out of doors.
Run out of doors. Selling a car without doors is a pretty rough sell, right? So probably going to stop making them. All right. So this is our doors in this case would be our, help me out here.
Limiting reactant.
Thank you, limiting reagent or limiting reactant. Okay. We would have some leftover engines. We would have some leftover tires for the next day. Okay. Does this make sense to you guys?
Yeah.
That should be reasonably easy for you guys to visualize. Okay. If you struggle with these when we come to chemical equations, and I'm not going to say it's as easy, it's not, okay? But I want you to come back to this example to see what we're talking about, okay? Use the tire example to kind of get yourself back on track. All right. Let's tackle a chemical reaction. Okay. Okay, so I want to get through this with you guys and then we'll call it good. Or are you guys wanting like 2 more hours of this? Or you think you're good? I think you guys are good. All right. Okay. So looking at a chemical equation, okay. So our chemical equation here says 4 NH3 and 7 O2s gives us 4 NO2s and 6 H2Os. Okay. Reminding you of what that means or how we interpret this then, we can interpret it 2 ways. You can say 4 molecules of NH3 and 7 molecules of O2 react to give me 4 molecules of NO2 and 6 molecules of H2O. Or what? 4
Moles of NH3.
4 moles. Moles of NH3 reacts with 7 moles of O2 to give me 4 moles of NO2 and 6 moles of H2O. Okay. Most typically, when we're going to work these problems, we're going to work with mole amounts. Usually you don't react 5 atoms of this with 20 atoms of that or whatever. You're using gram quantities of the stuff. Okay, so what we're going to do is we're going to say, okay, I have 200 grams of NH3. I have 500 grams of O2. Based on that, I want to know what the limiting reagent is. Okay. All right. So going back to our car example, again, your fundamental question should be, how much product can I make? Okay. So what do? I have 200 grams of NH3. What do I want to know based on that 200 grams of NH3? How much
H2O you can make?
how much product can you make, right?
How much product? Yeah.
In this example, unlike the cars where you only had one product, here you got 2 products. It doesn't matter which product you pick. So it looks like in our calculations, we picked water. You could just as easily have picked NO2. It doesn't matter. So from your 200 grams of NH3, your question is, how much product can I get based on that 200 grams of NH3? So our scheme is to do what? Go from grams of NH3 to
Moles.
moles of NH3. Can we do that?
Yep.
Yes. Based on the molecular weight off the periodic table, right? Okay. Then once I have moles of NH3, sort of think of it as the chemicals in the reaction can kind of talk to each other then. They talk to each other either in terms of moles or molecules. And my balanced equation tells me what? I get 6 moles of H2O for every 4 moles of NH3. Coming from the coefficients in the balanced equation. All right. So grams of NH3 to moles of NH3. Moles of NH3 to moles of H2O. And we're just going to stop there. You could go to grams of H2O, but it just adds an additional step. All right, so crunching through that, what do we get? From our 200 grams of NH3, we could possibly make what? 17.65 moles of H2O. Okay. Now what? We have some oxygen. What do I want to know about that oxygen? Fundamentally, I want to know how much product can I get from that oxygen. Okay. Now, since we did water for the first one, we want to do water for the second one. So we're comparing apples to apples, not apples to oranges. Okay. So if you do moles of water here, do moles of water here. Your process is going to be the same in terms of you're going to go from grams of oxygen to moles of oxygen. Hopefully we've established we can do that, right? That's one of our important conversion factors. And then for moles of oxygen, you want to go to moles of H2O. Again, that is a product, and that's the product we picked up here. So we do want to pick the same product. So again, we're comparing apples to apples. Don't do H2O for one and NO2 for the other one because it might give you the wrong answer. Okay. All right, so let's look at these numbers. Again, crunching through for the 500 grams of oxygen, what we calculate is we could possibly make 13.39 moles of water. Okay. So look at these numbers and realize what it tells you. From the 200 grams of NH3, I could possibly make 17.65 moles of water. From the 500 grams of O2, I could possibly make 13.39 moles of water. Okay, my question to you then is, do I make 17.65 grams? Do I make 13.39 grams? Do I add them? Do I subtract them? Do I take the fourth root of them? What do I do? What do you get?
You get 13.39 moles.
You get 13.39 moles of water, okay? What happens when you get 13.39 moles of water?
You've lost all your oxygen.
Your oxygen's gone. Oxygen's gone, your reaction's done. If you don't have any more doors, you can't make any more cars. If you don't have any more oxygen, you can't make any more NO2 or H2O, okay? Same thing. All right. Again, a little more complicated, but you get the idea. Okay. So again, what this is telling us, from my 200 grams of NH3, I could possibly make 17.65 moles of H2O. From my 500 grams of O2, I could possibly make 13.39 moles of H2O. What happens? I make 13.39 moles of H2O. When I get to 13.39 moles of H2O, my oxygen's gone. My oxygen's gone, my reaction stops. What does that tell us? Oxygen is my
Limiting reagent.
limiting reagent. And the other thing it tells us is, if that's your limiting
I have a
reagent,
question.
yes. Go ahead.
When you were saying that all of the oxygen was gone, can you re-explain that?
Okay. So are you with me on this? From 200 grams of this, we calculated we could possibly make this.
Yeah, I understand how you did all the equations and stuff, but what does the 17.65 mean in terms of like the broad equation up top?
I'm going to try to answer you, and then you tell me if I answered your question or not. Okay. So from the
Okay.
if you have 200 grams of NH3 based on this reaction, you could possibly make that much water. If you have 500 grams of O2 based on this reaction, you could possibly make that much water. You're never going to get here.
Okay.
You're never going to get there, because just like for cars, you need engines, tires, and doors. You need everything, right?
Mm-hmm.
From the 200 grams of NH3, you could get there. From the 500 grams of O2, you could get there. Once you get there, your reaction's done, because that's going to use up all 500 grams of oxygen.
Didn't you also use up the 200 grams of NH3?
You wouldn't have used all of it, because you could have possibly gotten that far. So we'll get into that calculation. You're actually going to have some leftover NH3. Does that make sense to you?
Okay.
Because if you only make 13.39 moles and you could have possibly made 17.65 moles, you're going to have some of this left over.
Mm-hmm.
Does that make sense?
Yeah, in the equation in the car problem,
Yes.
so like you are making everything. I understand that the H2O is basically the cars, but once you got like the 40 doors was the one you were working with, and you simplified it out to 20 cars.
Yes.
Like, I don't understand how you're really doing that for the NH3 and the O2. Like, it's not the same number.
Well, water is a product, right?
Yeah.
So it's on the product side. It's a product. Fundamentally, the question you should be asking yourself, whether it's the cars or the chemical equation, is how much product can I get from these starting materials?
Okay.
So you crunch the numbers, and that's what you get. That is a product. So that's how much product you can make based on the amount of NH3. That's how much product you can make based on the amount of O2.
Okay.
What makes it like the car equation is this mole to mole relationship. The 4, the 7, the 4, and the 6 are similar to the 1, the 4, the 2, and the 1.
Okay.
Does that make sense?
Yeah.
Okay. So again, just make sure you're with me. From the 200 grams of NH3, you can possibly get 17.65 moles of water. From the 500 grams of O2, you could possibly get 13.39 moles of water. You never get here. Just like on the cars, you never got to 40 cars because you run out of doors. In this case, you run out of oxygen.
Okay.
So oxygen is your limiting reagent. So you never get here. And again, we'll get to this. What that implies is you're going to have some leftover NH3. But all of your oxygen is used in that process.
Okay, that makes sense.
Okay.
I understand.
Good. Okay. Um, okay, so based on this equation, what's going to happen? Am I going to make 17.65 moles of H2O, or am I going to make 13.39 moles of H2O? I'm going to make 13.39 moles of H2O. Okay. I'm going to have no oxygen left. So the important number, once you do this calculation, this is the important number, 13.39 moles of H2O. What I'm going to do with that number next is I'm going to figure out if 13.39 moles of water is involved. I can relate that to all the other chemicals in the reaction. Okay. So I'm going to take my 13.39 moles of water, what I calculated based on the limiting reagent. I'm going to convert that to grams. From 13.39 moles of water is the same thing as 241.0 grams of water, using a mole to gram conversion. I can't believe all 30 of you are still with me. We're almost done, you guys. Hang on, okay? All right, so from my 13.39 moles of water, I can convert to grams of water, and using your gram to mole conversion from the periodic table. And so I calculate, I got 241.0 grams of water. From my 13.39, it says grams there, that should say moles there. So if you have these printed out or you're writing these down, change that to moles of water there, that's important. From moles of water, you go to moles of NO2. Remember, NO2 is our other product. Okay. From moles of NO2, I go to grams of NO2. And what I'm getting here is from my 13.39 grams of water, or I'm sorry, 13.39 moles of water. In making my 13.39 moles of water, I'm also going to make 410.6 grams of NO2. Okay? Because based on the equation, for every 6 moles of water I get 4 moles of NO2. That's coming from the coefficients in the balanced equation. All right. So I've got water here. I know I have no oxygen left. I've got NO2 here. What else happens with the 13.39 moles of water? You can also relate that to moles of NH3, which is a reactant. And then from moles of NH3, you can go to grams of NH3. Now, NH3 is a reactant. What does that mean in terms of H2O and NO2? How is it different? What's happening to a reactant as we proceed in the reaction? What's it doing? Are we making it, or is it going away?
It's going away.
It's going away.
Product.
Okay, so when you run through this calculation, you get the amount of NH3 involved, but that is the amount of NH3 that is used in the reaction. Because it's a reactant, it's going away. We're making this water, we're making this NO2, this is going away. The oxygen's also going away. In fact, it all went away. All right, so we use up some NH3. That's the amount we use up. We don't care about how much we use. We want to know how much is left. So what do? We started with 200 grams. Remember, that was given in the problem. We calculated that we used up 151.8 grams of NH3. We will have 48.2 grams of NH3 left. All right. Now, what do we know is true? One of the things we know is true is conservation of mass. Conservation of mass says what? Mass in equals mass out. If I start with 50 grams of stuff, I'm going to end with 50 grams of stuff. If I start with, what did I start with? I started with 200 grams of this and 500 grams of this. I started with 700 grams of stuff. Tell me what's true at the end of the reaction.
You should end up with 700 grams of stuff.
I will have 700 grams of stuff, or I better have 700 grams of stuff. So what do? You have no oxygen. You have 410.6 grams of NO2. We calculated that right here. 241.0 grams of H2O calculated here. And I have 48.2 grams of NH3 left over. That gives me 699.8, which is what? Darn close to 700 grams. So I started with 700 grams. I end with 700 grams. That's the nice thing about these problems is you can always check your answer. Because whatever you start with in terms of grams should be what you end with. Okay. Does that make sense to you guys?
Yeah.
Okay. All right. Questions on that? Okay. What I'm going to do with you guys then is, give me a second here. I got to write some stuff down. I'm going to give you a homework problem to do. We're going to use the same equation. All right. I'm going to give you. So you're going to deal with the same equation. And I'm going to say, let me change here. Let's say you have 300 grams. Reacts with 1,000.0 grams of O2. Find the limiting reagent. Okay. Find grams of each substance present after the reaction. Okay, so we're going to use the same equation we used in our example. We're just going to have different amounts of stuff. I want you guys to run through that. I want you guys to run through that for Thursday. And we'll go through that calculation and see what you should get. What do you know is true? What should be true at the end of your problem?
It should be equal to 1,300 grams of the substance.
Yeah, you should have 1,300 grams of stuff when you're done. Okay. Now, you're going to lose some NH3, you're going to lose some O2, you're going to gain some NO2, you're going to gain some H2O, but what you know is you should have about 1,300 grams of stuff at the end of the reaction. Okay. Don't get too excited if it's off a little bit due to rounding. Don't worry about that. So if you get 1299.6, it's fine. But if you get 3,000 grams, obviously that's a problem. Okay. I'm going to call that a good stopping point. I'm a little afraid. You guys have any questions?
No.
Okay. How do you think it went today? Again, I'm a little afraid.
I think it went good.
Okay. Trying to get back to this. There we go. Okay. Now I got you all back here. Questions, comments, concerns? Okay. Just again, I think you guys will get more out of lecture if you're able to be here. That said, I understand that you won't always be able to be here. Do the best you can. And this is kind of how things are going to go from here on out. So we're going to call it good. Last chance for questions. Going once, going twice. All right, I'm gonna sign off for the day then. I will see you Wednesday. Go ahead.
Sorry. The notes with the errors in them, is there any way for you to correct that, or do we just need to write it down?
So,
I'm just juggling a 2-year-old, and when I go back to look at those notes, I don't think I'll remember the other mistake that was in there.
I got it.
I know the one with moles instead of grams, but I can't remember that other thing that you said, but I can compare with someone else if it's
Right.
easier.
So I needed to get these up as quick as I could. So that's what I did. I will go through them more.
Okay.
I will go
Oh,
through
the other
I'll go through the next set more carefully and correct the mistakes before I post them.
Okay.
You can always go back and watch the video. I know
Oh,
that's
yeah.
not great.
No, that's right. I forgot about that.
You can. So what I would do if I was you guys is I would have a little notepad or something to kind of scratch down notes, and then you could say something like, I don't know if it times the meeting for you guys or not, but you could say, or just make a little notation, hey, I need to make this correction. Okay. So I will try to correct them for the next set. All right. Did someone else have a question? Yeah, there was somewhere it was labeled, I think there was a H2 or 3, 2H, something with hydrogen was not labeled quite correctly. Okay. All right. Any other
I got a
questions?
question real quick.
Yes.
Yeah, I got one. So for lab on Wednesday, is that going to be kind of like these lectures, like recorded, or is it we have to be online for those?
Okay, so it'll be recorded. What I'll tell you is the video for that is posted. So there's a video for the titration lab. There's actually 3 videos
All right.
for that one. The idea is that you guys watch it before we meet. We will meet at 1 o'clock. Okay, so at 1 o'clock, you'll have a chance to ask questions about the lab. I may go over some things with you that just aren't easy to explain or whatever. You'll have a chance to ask questions, and then I anticipate that lab also being due the following Wednesday to kind of get us back on track of due the week after we do it. Does that make sense?
Okay. Yeah, but the questions everyone asks when you record that, you're going to record that and put it up too.
That'll be recorded and it'll
Okay.
be available if you're not able to be there live.
Okay, awesome.
Okay. Anything else about process or anything? I know some of you came in a little late or whatever, so I went through some of that stuff. Or did you think of anything as we were going through? All right, I'm going to call it good. I'm way more relieved than you guys are that this is over for today. But I appreciate you guys. You guys are more flexible than me, more adaptable than me. So based on lab yesterday and what we did today, this is going to go okay. I don't think it's going to be great, but we're going to settle for okay. All right. You guys, again, hit me with emails or whatever. Other than that, I will see Wednesday lab people tomorrow, and I'll see you guys back on Thursday. All right? You guys have a good day.
You too.
Thanks, you too.
You too.
All right. See ya.